So we're trying to write down the Hamiltonian equations and solve the equations of motion for a mass that is forced to stay along the perimeter of a cylinder, where the only force acting on it is some central force negative kr in the r hat direction. Before we can start doing Hamilton's equations, we actually have to solve the Lagrangian first. So part one of this is going to be solving the Lagrangian and then using a coordinate change to get the Hamiltonian in terms of the Lagrangian. So Lagrangian is given by kinetic energy minus potential energy. In Cartesian, we have 1/2 m times the velocities of x, y, z, respectively, squared. So what we're going to do is we convert it to cylindrical, so r cosine phi. One of the parameters of this problem is that it is confined to be on the surface. So anywhere that we would see little r, we could put big R. This should be big R. Will be big R, and then we don't have to deal with partial derivatives in terms of r. So r cosine phi, r sine phi. We take the derivatives. X dot is going to be negative r sine phi. Cosine becomes negative sine. And then a phi dot, which comes from the chain rule. Same thing over here for r cosine phi, phi dot. We plug this in, and we get negative r sine phi, phi dot squared plus r cosine phi, phi dot squared plus z squared, all times 1/2 m. What we're going to get here, when these multiply out, we'll get r squared in front. The negative is canceled by the squared. But we'll get sine phi squared plus cosine phi squared, and that is equal to 1. Sine phi squared plus cosine phi squared is equal to 1. And so that simplifies this down a lot, and we're left with r squared, phi dot squared in the middle, and then the z dot stays the same because in cylindrical coordinates it doesn't do anything to the z component. So now we have our kinetic energy term. Fantastic. We need to get our potential energy term. The only force acting is this central force, which means we actually don't have gravity. But we do have a potential energy because it's not as close to this force as it could be. So we're going to use the classic force is equal to the negative gradient of potential, which means that negative kr, the integral of negative kr with respect to r, dr and dr hat, is going to be a negative gradient. The gradient and the integral are going to cancel out. These negatives cancel out, and we're going to get the integral of kr, which is very simply 1/2 kr squared. And so we get that the potential is 1/2 kr squared, which means that we can write the whole potential, which means we can write the whole Lagrangian equals 1/2 kr squared. The whole Lagrangian can be written as 1/2 times m times r squared phi dot squared plus z dot squared minus, because it's k minus v, minus 1/2 kr squared. However, we don't have, the Hamiltonian is expressed in phi dot and z dot, which we'll see in part B. And this term does not have this at all, which means that it is actually, they are ignorable. So we don't care about the potential, and we can disregard that and care only about this expression, which is what we are going to use to solve the Hamiltonian. Okay, so now that we have the Lagrangian, we are able to use the Hamiltonian. Before we set up the Hamiltonian, we're going to do two things. We're going to say that the momentum with respect to phi and z are the Lagrangian, the partial of Lagrangian with respect to phi dot and z dot respectively, which gives us mr squared phi dot mz dot. Hamiltonian is defined, try to highlight this, to be phi dot, momentum of phi dot, plus momentum of z dot, minus the Lagrangian. So that's why we found the Lagrangian. So we're going to cleverly write these two things in terms of their momentums, and then we're going to subtract the Lagrangian. We distribute this out so that we can apply each of them. Some of the m's are going to cancel, some of the r's are going to cancel, get the m cancel here, and we get a final expression for a Hamiltonian that is momentum in the phi direction squared over 2mr squared plus momentum in the z direction squared over 2m. Now, the last part, what we're looking at the equations of motion is we're trying to say, okay, well, the change in phi dot, is the partial of the Hamiltonian with respect to phi, of which it is 0, because there is no phi in the Hamiltonian. And then in the z dot direction, it's the partial of the Hamiltonian with respect to z, of which there is 0, because it's independent of z. And so this seems weird. It almost feels like something's wrong. And if we write out our equations of motion, we're going to get some constant, phi naught, plus our Hamiltonian term, p phi squared over 2mr squared. And then we have pz squared, z in the t direction is some initial z plus pz squared over 2m. And those are equations of motion, which come from here, and some initial constant. And this seems weird. And it's almost an unsatisfying answer. But if we look in using hindsight, we say, okay, we're confined to this point on the surface, and the only thing pulling in is central, so it's a constant central force, meaning it's centripetal force. So we essentially are looking at a uniform circular motion ball on a table with a string, except that this ball is able to move around in the z direction, and if it has some starting z naught, it will just continue to spiral upward in a helix. In the same way that if it has some omega, it will continue to go around the circle in the same way. And it's an unsatisfying answer because it's sort of an unsatisfying question that just is a little bit redundant and shows us uniform circular motion, but we just add a z direction. Very, very quick amendment. There should be t's here. Thank you.